Okie doke. So now we can get into solutions. So we've talked about solutions at the beginning of the semester, but I just want to go through a little bit of the background again to make sure that we have incorporated some of this new information about intermolecular forces into our idea of how solutions are formed, right? So there's two basic components of a solution. The majority component of a solution is called the solvent. The minority component is called the solvent. Solutions are formed because of intermolecular forces, right? I think up to this point, we've pretty much discussed solutions as being ionic solids dissolved in water, right? Pretty exclusively. But we're going to broaden our definition of solutions to be any homogeneous mixture, right? What do I mean by a homogeneous mixture? Evenly mixed or uniformly mixed. You can think about it as being a mixture that has no discernible phase separation, right? Meaning the mixture looks and is chemically uniform throughout. Does that make sense, guys? Yes, Danica, I understand. Cool. So I think before, when we were talking about solutions, we were calling the solvent the thing doing the dissolving, and the thing that is being dissolved. But now we're going to broaden that definition to the solvent being the majority component and the solute being the minority component, right? The reason being because when you get into certain types of mixtures, especially liquid-liquid mixtures, it doesn't really make sense to call one of them a solvent and one of them a solute when the only thing that makes one of them a solvent and one of them a solute is their proportionalities. Does that kind of make sense? So we have to broaden this definition in order to look at these different kinds of solutions. So we have gas-gas solutions, so air being the most common example of that. Any kind of mixture of gases would be a gas solution. We have liquid solutions, so we could have gas dissolved in a liquid. So an example of that would be soda pop. We can have liquid-liquid solutions, an example of which would be vodka, ethanol, and water. Solid liquid solutions would be the ones that we're most familiar with, so some kind of salt mixed with water homogeneously. And then a solid-solid solution, which I think is kind of the weirdest one to think about, would be, an example would be an alloy, right? So it's a mixture of metals that are homogeneously mixed. So brass would be an example of this, steel would be another example, right? So what I want to make sure you guys know here is what the different types of solutions are and an example of each one, okay? I'm gonna start high-fiving myself when I ask you guys questions. Yes, Danica, we understand, we get it. Thank you, Maya. Okay, so I think we talked in chapter 5 briefly about this concept of entropy. You guys remember this? So we said that the driving force that makes gases spontaneously disperse to fill their container is called entropy. You guys remember this?
Yeah.
Cool.
Yes.
So entropy, again, is this idea that energy dispersal is more effective in system when you can spread out the energy over as many different parts as possible, right? So that kind of energy distribution is what gives us these entropic forces. So energy has a spontaneous drive to spread out over as large a volume or as many types of systems as possible or as it's allowed. This is also the driving force that makes solutions mix, right? So entropy is what makes mixing happen. This idea of entropy, if we have two gases separated by a membrane here, and then we remove that membrane, the natural thing that's going to happen without us doing anything is those gases are going to mix evenly, right? And that's entropically driven. The same thing happens with concentration. So we could set up a concentration barrier here where we have 0 concentration and some concentration of ions on the other side. As soon as we lift that barrier, we get this spreading out of charges, which gives us a uniform concentration, right? So this idea of spontaneous mixing is entropically driven. Okay, so we talked about solubility in chapter 4 as well. When one substance is able to be dissolved in another substance, we said that it's soluble. Salt, for example, is soluble in water. Bromine is soluble in methylene chloride. Methylene chloride being an example of a nonpolar solvent. When one substance does not dissolve into another, it's said to be insoluble. So oil being insoluble in water would be an example of that. When you're talking about a liquid-liquid mixture, we say that if the liquids are able to be homogeneously, that the liquids are miscible, right? So that's this term down here. The liquids are miscible. If you're talking about liquids that are not able to be mixed homogeneously, they are called immiscible liquids, right? So solubility limits are what we're going to be talking in this chapter. So the maximum amount of solute that can be dissolved in a given amount of solvent is called its solubility. Am I coming through okay, guys? Because it's telling me my internet connection's slow. You guys?
You're good.
Okay, cool. Okay, so one of the things that we talked about in chapter 4 was this idea of solubility as being this kind of binary, right? So we usually talk about solubility as being either something is soluble or it's not soluble, it's insoluble, right? And now we're going to really broaden that into more of a continuum, right? So there are things that are really soluble and there are things that are really not soluble or insoluble. And there's everything in between, right? So we want to know how this spectrum of solubility is regulated by intermolecular forces, okay? And what that means for the energy required to make things dissolve or gotten back when you dissolve. And then one of the other things that we'll talk about a little bit more in detail, solubility is a function of temperature and pressure, right? So the pressure, when would the pressure be, what kind of mixtures or what kind of solutions would be especially vulnerable to temperature, or excuse me, to pressure changes? You think alloys would be particularly sensitive to changes in pressures? My wall on the other side of the room and I feel like I'm talking into a desert. I want the water. It's way over there. What kind of solutions would be extremely sensitive to changes in pressure? I'm gonna make you guys answer me. Yes, gases, right? If you have a gas-gas mixture, then they're going to be, the solubility of a gas into another gas is going to be very much sensitive to the change in pressure. What else? So we have gases mixed with gases. What about gases mixed with a liquid, right? Would pressure change those solubility criteria? Think about what you know about soda pop. Yeah, right? The pressure you have to get, in order to get gases to dissolve in a liquid, you have to put them under pressure. Does that make sense, guys? So not all solutions are really sensitive to pressure, but for the most part, they're all sensitive to temperature. Okay. Coolsies. All right, and then we have this rule of thumb, will it dissolve? And we say like dissolves like, which basically means if you have similar intermolecular forces, then they will probably be soluble, right? So polar molecules like to be with ionic compounds and other polar solvents, and nonpolar molecules like to be with other nonpolar solvents or other nonpolar molecules, right? So like dissolves like. Okay, so now we're going to get into enthalpy of solution or heat of solution. So I don't know if you guys have ever noticed, and we haven't been in the lab for basically 100 years. So if you didn't remember this kind of stuff, then I wouldn't be surprised. But when we talk about dissolving things, right? Some we dissolve them be thermic, right? Meaning they put off heat. So an example of that would be something like sodium hydroxide. So when you dissolve sodium hydroxide, the container gets hot, right? So you can actually feel this exothermicity of sodium hydroxide dissolving. But less common is this phenomenon of an endothermic dissolution, where we have a compound such as ammonium nitrate, which when it dissolves actually absorbs heat from the surroundings, and so you get a cold, right? So now we're going to talk about how that happens. So in order to talk about that, we have to talk about the solution process, right? So the first step in the solution process is we have to break up the solvent-solvent interactions, right? So is this an endothermic or an exothermic step?
Sorry, what was it? I think it cut out a little bit.
It is an endothermic. So we're talking about solvent-solvent interactions here, right? So little green guys are our solvent molecules, and we have to break them apart in this first step, right? So that's an endothermic step. Anytime we're breaking stuff, endothermic. Does that make sense?
Yes.
Cool. And then the next step is breaking apart the solute-solute interactions, right? So let's say our solute in this case was an ionic compound, right? Then this would be the delta H of the lattice, right? Meaning we're breaking apart these ionic solids. Remember the lattice energy from chapter a million years ago? Chapter 8? Cool. Anybody? Lattice energy, enthalpy of the lattice? Coulomb's law?
Yeah.
Low. Okay, cool. Somewhere in the dusty parts of your brain. Cool. So this is one of the places where we're actually start using those lattice energies. Okay. So let's say our solvent in this case was water, right? What would these solvent-solvent interactions be that we'd be breaking apart? Not liquid. If we're talking about water, right? What holds liquid water together?
We're talking about the bonds?
Yeah, totes.
Oh, the hydrogen bonds.
Yeah, exactly, right? So here, the delta H that's required to break these water molecules apart is the energy required to essentially break up those hydrogen bonds. Everybody with me?
Yes.
Yeah. Cool. And then again, the if the solute, and this is just hypothetical, right? If the solute was an ionic solid, then this would be the energy required to break up that lattice, right? So which one of these is a bigger delta H? In my hypothetical example, water and an ionic solid. The solvent? So you think it would take more energy to break the water molecules apart than it would the ionic solid? Hydrogen bonds are strong, right? They're the strongest type of intermolecular force. But what's strong in an intermolecular force?
Intramolecular forces.
Yeah. And is ionic bonding an inter or an intramolecular force? Does that make sense, guys? So everything that we're talking about now is relative strength, right? And having it well categorized in your brain, which forces, which interactions are stronger, is really going to help you understand how these interactions are working. Does that make sense? That's what I'm trying to get you to think about in these examples. Cool? Cool. Okay, so we take, in this step 3, we're taking the solvent and the solute and we're mixing them together, right? So this step 3, is this endothermic or exothermic?
So
Exothermic, definitely. Here we're sticking things together, right? Sticking things together is exothermic, breaking things apart is endothermic. Does that make sense, guys?
Yeah.
Cool.
Yes.
So the delta H of solution, right, can be either endothermic or exothermic, depending on whether or not the sum of the steps here gives us a net negative or a net positive, right? Okay, so this is just a summary of what we were just talking about. So the delta H of solution, energy is required to dissolve. The solute breaking up is an endothermic, we're breaking stuff. Solvent breaking apart is endothermic as well, breaking stuff. And then the delta H of mixing is that third step, and that's exothermic, right? So here's that picture again. We have an endothermic step and and exothermic step, right? So whether or not we have an endothermic or an exothermic delta H of solution depends on how strong this interaction of mixing ends up being relative to the strength of the original solvent-solvent and solute-solute interactions. Cool? Okay, so here's an example of one of these. Pull apart, yes. So when pulling things apart or breaking stuff, endothermic, yes. Yeah. So here's an example, oops, sorry, of the steps involved. They kind of simplify this into 2 steps. So we have the ionic solid being broken up here. So if this is sodium chloride ion, I'd have the sodium chloride ions being broken up by adding the lattice energy. So the lattice energy, the enthalpy of the lattice is something that you could look up in a table, right? It's not something you have to calculate. But this energy is usually given as an exothermic value, meaning a negative value, because that's the energy that you get when you assemble the ionic solid. But in this case, we're trying to break apart the ionic solid, right? So we need to add this lattice energy. Does that make sense?
Yes.
Cool. Then our step 2 and 3, where we have the ions mixing with the and the solvent-solvent interactions being broken up, are combined into one step, which is called the heat of hydration, okay? The heat of hydration is essentially, okay, if we're adding these ionic particles into the solution, we have to first separate the solvent-solvent interactions a bit, and then we get this exothermic attraction between the solvent and the ions, right? Those are those dipole, ion-dipole interactions, right? We talked about in chapter 10. You guys picking up what I'm laying down? Yes, Danica. I know, cool. So you can see that the energy of the lattice and the heat of hydration are pretty free together, right? So this delta H of solution for the dissolving of NaCl is endothermic or exothermic?
Endothermic?
Yeah, it's endothermic, but just barely, right? So I don't know about you guys, but I've never put salt into water and then noticed it heat up or get cold, right? Excuse me. Does that make sense? So this is obviously a very small amount of energy required to get sodium chloride to dissolve, right? Where does the energy come from to get this ionic solid to dissolve? Let's say we're trying to dissolve it in water, right? Like this example. Where would this kilojoules per mole come from? What kind of energy is always present naturally? Potential, kind of. I'm thinking about on our planet. So you're on other planets, this might not be the norm. Pressure, kind of. I'm thinking more about thermal, right? So generally speaking, as long as you're not in Antarctica, right? There's usually some amount of thermal energy present in any solution. And so this 4 kilojoules is measured by the solution is by taking heat, the solvent, right? Does that make sense, guys?
Yes.
Cool. Questions about that? Cool. Okay, so here's another way of representing these delta H of mixing, the delta H of the lattice and the delta H of hydration. So when we were talking about our original example of sodium hydroxide, right? The sodium hydroxide relatively small lattice energy, which we'd have to add to get it to go into its respective ions. But when we hook it up with water, we get a lot of energy back, right? So this is a much delta H of solution, negative delta H of solution, right? This is why our our container gets so warm when we try and dissolve sodium hydroxide. Does that make sense, guys? Cool. Just to kind of give you guys a little bit of assurance here, the delta H of the lattice and the delta H of hydration would be given to you if you were asked to solve for the delta H of solution. But you could also be asked how much energy would be required to dissolve X amount of this solute, right? That would be another type of question that we could ask with this enthalpy. Make sense? Cool. And then we had our ammonium nitrate, right? The delta H of the lattice here in this case is really, really high. And the amount of energy we get back from mixing is relatively low. We end up with this delta H of solution that's 25 kilojoules per mole. So relative to our 4 kilojoules from the sodium chloride, this is a really increase, right? And that's why you can feel this, this container getting cold, whereas you wouldn't be able to feel that with sodium chloride necessarily. Does that make sense, guys? Cool. Oops. Okay. So we talked about this. The heat of the solute is equal to the opposite of the lattice energy, and the heat of the hydration is just combining the delta H of the solvent and then the delta H of mixing. And again, the delta H of mixing is those attractive forces between the ion and the water. So here's another example, potassium fluoride. So I don't know if you guys remember, but I'm just going to remind you real quick when we're talking about lattice energies, there's 2 things that are going to modulate the magnitude of the enthalpy of the lattice, right? Those 2 things are the ion charges, right? So larger charges are going to have larger lattice energies. And particle size is inversely related, right? So if you have smaller ions, there's going to be more of them stuck together in a smaller area, and so the delta H will be larger, right? So smaller ions, larger delta H, okay? So looking at our sodium chloride, we saw that the enthalpy, the lattice energy here was 788 joules per mole. Getting into potassium fluoride, it's 821. So it's just slightly bigger. Why would that be? So which is bigger, fluoride or chloride? Chloride is bigger, right? Bigger means lower energy. So the reason why this delta H of solution, the lattice is, the delta H of the solute, or the lattice energy is bigger in this case, is because fluoride is smaller than chloride, okay? Just something to think about in terms of solubility interactions. Okay, so then when we combine the ions and the solvent with this delta H of hydration, we get an overall delta H of solution of positive 2 kilojoules per mole, right? So again, really, really small numbers. We talked about these ion-dipole interactions and how they, how ions become hydrated. We talked about that in chapter 4. Okay, so, all right, so one thing I want to get into is talking about solubility curves. So when we're talking about whether or not something is soluble, we have this representation called a solubility curve. I'm going to go back to the slides that we just skipped in a second, but I want to introduce this right now when we're thinking about delta H solution. So we said that sodium chloride, NaCl, has a delta H of solution of 4 kilojoules per mole, right? The line that's represented here, you can see that small delta H in the slope of this NaCl curve, right? So smaller slope means smaller delta H, okay? Is the slope of the NaCl curve positive or negative? Positive, right? Indicating that this is an endothermic delta H of solution. Does that make sense, guys?
Yeah.
Cool. So which one of these compounds has an exothermic delta H of solution? Yeah, the cerium sulfate. Does that make sense, guys? So this guy right here is going to have the only negative delta H of solution on this curve, right? It's not the only thing that has a negative delta H, but it's the only thing on this particular representation that does. Does that make sense, guys?
Yeah.
Cool. So being able to interpret this graph is one of the number one and probably hardest things that you'll have to do in chapter 13. Okay, so all of the information that we're talking about is really neatly summarized in these beautiful tables, and I love them. So you're definitely going to have a question on an exam that deals with kind of curvature, right? So looking at the curvature of some of these other slopes, right? Would you say that potassium nitrate or potassium chloride will have a larger delta H of solution? Why KNO3, Tyler? Bigger slope, absolutely. That's exactly right. Does that make sense, guys?
So yeah.
Okay, cool. So, so those are the kinds of questions that I could ask you qualitatively about a graph like this and what it says about the delta H of solution, okay? Beep, beep, beep. Okay, so one of the really important topics that I think we've kind of touched on in other chapters, and this is kind of where we're going to end today, is this idea of equilibrium, right? So we've talked about dynamic equilibrium in the case of solution formation. We talked about it in terms of certain types of reactions, especially weak acids, things like that. So this of equilibrium is that the molecules and interactions between particles never stop happening, right? We can think about the state of an unchanging system as being a steady state, right? But it doesn't mean that there's nothing happening, right? There's always thermal energy, there's always motion, there's always things happening, right? So when we talk about equilibrium, we're not saying that that this is a static system. We're saying that there's no discernible change in equilibrium, right? And solution equilibrium is no exception to this. So when we talk about something, right, this spectrum of whether or not something can be soluble or can dissolve or not is really determined by the solution equilibrium, okay? So when sodium chloride is added to water, the sodium chloride ions begin to dissolve or dissociate. the sodium chloride is going to form these sodium and chloride ions, but there's always going to be a small amount of recrystallization happening, right? So the dissolution or the dissociation is the ions being broken up, and the recrystallization is the reformation of that solid, right? When the rate of dissolution and recrystallization has become equal, that's when you reach solution equilibrium, okay? So the important thing here is that we're talking about the rates of dissolution, okay? Excuse me, of dissolution and recrystallization. We're not talking about concentrations, okay? Do sodium chloride solid ions, or excuse me, solid molecules exist in this solution? What do you think? In a perceptible way. What do you know about sodium chloride? Is it soluble or insoluble? Sodium chloride, soluble, insoluble? Soluble, right? Everybody comfortable with that? Why? What are the two basic rules that we asked to memorize in chapter a million years ago about solubility? What things are always soluble? Sodium is always, but why sodium?
It's a group 1 metal.
Exactly, Brooke, exactly. It's a group 1 metal, right? So group 1 metal ions are extremely soluble, right? So they're very good at breaking up with their ionic partners. The other big one that we said to remember was nitrate, right? Any kind of nitrate is going to be, anything paired up with nitrate is going to be very soluble, right? So if you know that sodium chloride is very soluble, do you think that the equilibrium favors ions more or the solid more in this case? Ions, absolutely. Almost completely ions in this case, right? So we said that sodium chloride, because it's a strong electrolyte, almost completely breaks up into sodium and chloride ions. Does that make sense, guys? But not all solids are like that, right? Some solids are slightly soluble. If things are slightly soluble, then that means that this equilibrium is a little bit less sure, right? We don't know whether it lies on the side of the ions, oops, or on the side of the solid, right? Does that kind of make sense? This is going to be huge when you come into 201, okay, guys? So this is pretty much the first 4 chapters of 201 are all about solution equilibrium, okay? Questions about this? Cool. So I just want to mention one more thing. I think the sodium chloride example of solution equilibrium is kind of a bad one, mainly because the equilibrium lies so far to the product side in this case that it doesn't even really seem like there's any back and forth, right? But there's one big example from chapter 4 that we talked about where the aqueous version of something doesn't necessarily break down into ions. You guys remember what that was? It was that was really hard to get right when we were doing the total and the net ionic equations. What's the only aqueous species that won't break down in the net ionic equation? Weak acid. Exactly. Yeah, so does that make sense, guys? So these weak acid equilibria are a huge part of Chem 201, right? So the solution equilibrium is kind of weird when we're talking about something like sodium chloride, which is super soluble. But when we get into weak acids and other kinds of weak electrolytes, that's when this solution equilibrium becomes really, really important to understanding chemical reactivity and how many ions are going to be in solution, okay? Okay, I think